Welcome to Aiven. For those of you who haven't been here before, we are, well, my name is Amy. I think I should start with that. I'm Amy, I'm a developer advocate here at Aiven. And with Aiven, we are a financial technology platform. We offer a solution for payments end-to-end. Think of any part of the process of payments. We take care of that. And of course, we have customers around the world. And I think what's important for you to know is that we have 3 tech hubs. So around the world, we have offices, or we have what we call tech hubs, where we have our engineers work at. And there are 3 of them. In Chicago, in Amsterdam, we're in one of them, and then in Madrid. I've talked about where we are, who we are. This is how we build what we build. I have the links of these logos in the next slide, so don't worry about figuring out what they stand for. But our tech stack, we offer, this is not a limited list. These are just some of the things we use at Aiven. Postgres, Java, VJS, Linux, and they're some of the most popular ones. But yeah, this is how our tech stack looks like at the start, at a glance. And I wanted to end, welcome to Aiven. We are hiring, of course. Of course, there are roles that, especially for our niche, for those of us who are here, data engineering, we have roles in Madrid, in Chicago, the tech hubs I mentioned. We are hiring, so you can refer, the website is there, refer your friends, you could also apply, so if you want to. So I think I'm done blabbing with we'll have you. I'll hand it over to Flo. Welcome again and have a very nice time.
So, thank you everyone, and welcome to the Amsterdam Open Source Data Infrastructure Meetup. This is the second meetup of this kind, and we're going to talk about ClickHouse today. You know that, because you registered for this event. Really want to thank Aiven for hosting us. Thank you so much, even though you had no idea how many people would show up, or any event details really. For this event, we have a code of conduct, so please, if you are not familiar with any code of conduct or this one in particular, please check it out at aiven.io/community/code-of-conduct. If you have any concerns, please bring them up with me. I'm one of the organizers. If you feel like you can't bring it up with me, please either go to Anna or one of the wonderful people at Aiven who can probably help you further. All right. Well, a little bit of promotion. We have a couple of free plans available forever. So that's cool. For Postgres and MySQL and Redis, they're quite generous plans. If you want to play around with those tools, please do so. Yes, if you people taking pictures of this slide. Right. We also have a startup program. So if you are in a startup, if you're thinking about maybe doing a startup, this is our way of giving back to the community. So it might also be really interesting to give away a ton of credit and then also some technical expertise might you need some. Right. We have a next meetup planned because, we're hosting this one now, so we need a next one. So June 20th, we'll meet in ClickHouse CTO. We'll talk about metrics and alerting and that kind of stuff. So a little bit Prometheus, Thomas kind of stuff. So if that's your jam, join us on the 20th of June as well. All right, and then feedback is a gift. So if you like it or not, but definitely if you like it, please leave some feedback so I can continue doing these meetups. That would be really happy. All right, I think that's it for me. Oh yeah, my name is Floor. I work at Aiven. I do community stuff like this. And I would love to invite Olena up on the stage, who's my colleague, and we'll talk about ClickHouse.
Cool, amazing. Hello everyone, my name is Olena. I work at Aiven, where we help and contribute a lot into open source technologies. And today I wanted to talk about one of those technologies, which I find to be just so cool and so unusual in many different ways. It is a data warehousing solution And some of the reasons why I am so excited about this technology, I would like to share in this presentation. And our journey today will look like this. We'll start by talking briefly about the challenge of storing big amount of data long term, and in particular we'll talk how analytical processing is different from using data for transactional purposes. Then we'll look at how ClickHouse fits in this scenario, and I will stop at some of the architectural characteristics of ClickHouse, which might be different from other solutions you already know. After that, we'll move to a demo, and then we'll talk about things you need to be aware of when using ClickHouse, so you don't get into data swamps and avoid pitfalls. And finally, I will leave you with some additional materials you can use to start your own journey with ClickHouse. So data is everywhere, and our life wouldn't be the same if not for the amount of data which is involved at every step of our daily activities. And this involves some obvious scenarios like online services, measurements from different IoT devices, weather data, and for the products that we build, the more data we can handle, the bigger value it can bring, the better predictions, the better analysis, understandings we can retrieve, and therefore better business decisions we can make to move us forward. However, in the past, when working with data, what happened, we often processed what we needed, then selected bits and pieces, stored them in some database, and sadly, we had to throw away all the rest of data because storing all raw data felt unfeasible, not only because of the storage volumes, something very strange, it's my voice, but also because of the processing powers which are needed to navigate that amount of data later in time. And especially this is relevant to the data which can be used for analytics. So for example, imagine event-driven system where we look at the data from the prism of continuously coming events. And that timely data help us process real-time information and make fast decisions. But the question is, what to do with that data in a month, in a year, maybe in a decade? How can we store it long-term and use it for future analytics? And there is a variety of storage tools which we can use. However, when it comes to big volumes of data, which needs to be scanned in big chunks, aggregated and used for complex computations, and all of that, of course, needs to be fast. Nowadays, no one wants to wait. We need to be very careful what kind of tools, what kind of storage we select so that it can handle those types of requests. And this is not the moment where you want to rely on a Swiss Army database such as Postgres, which we love and respect dearly. However, to solve this problem well, we need to use specialized tools. And to understand why we need a separate solution, let's very briefly look at two different types of systems: online transactional processing and online analytical processing. And what I want you to do is to pay attention to the granularity with which these systems process the data and to the types of operations which are prevalent in these systems. And let's start with OLTP. And let's imagine that you are running an online shop, and you have information about each individual user in your online shop, such information, their address, their names, their payment preferences, and so on. When you need to do an action, so user makes an action, for example, updates address, you need to go to the database and find that information that row quickly, read it and update it. So we need to send a request to target specific rows in the table in the database. And we find often those rows by customer ID, and technically you can ignore the rest of the rows of other customers. So it's very narrow and precise operation, and obviously to keep the data consistent, because you might want to change not one tables, but several most probably, we rely on transactions. Now let's compare this to a different type of system. For example, for this online shop, you want to keep the analytics. You want actually to understand the behavior of the users of your system, what kind of products they enjoy, what kind of pages they visit. So for this, we don't think any longer in terms of individual users, but rather we are focused on computations and data aggregations. So the focus shift from finding and updating individual rows into processing millions or even billions of rows. And what is important, usually only the fraction of fields is important. So here we are not really processing the complete rows. We are focusing on certain fields when we need to make those computations. And also, unlike of the OLTP example, here we often don't update the past data. So because of these scenarios, they're so different. Of course, we can create solutions which target this difference and which make each of the solutions efficient. And in fact, building a highly performant solution for online analytical processing was exactly the motivation behind ClickHouse, and as a result, it can process billions of rows and tens of gigabytes of data per second, which not only by far beats OLTP solutions, but also performs really well comparing to other OLAP systems. And to achieve this performance, ClickHouse has to think outside of the box, literally turning around some of the concepts which we are familiar with. And if we look at the most prominent features and characteristics, and this is a screenshot from the documentation of ClickHouse, amazing documentation, by the way, it's difficult to miss, so many of those different characteristics are focused on performance and efficiency. So to give you a general understanding how ClickHouse works, let's look at a couple of those characteristics. And let's start with how data is structured and stored. So when we look at traditional transactional databases, for example, Postgres or MySQL, they store data in a row-oriented approach. So they store data row by row. And this means that even if you select some cells in that row, you still have to scan the complete row. Also, as a consequence, you have different types of data stored in a single file on the disk. And in most of the cases, it's totally fine. However, when we are talking about analysis and computation, which relies on aggregation and grouping of the data, this is quite inefficient to store it row by row, because we have to read significantly more data and go into significantly more details than is actually needed for our analysis. That's why it's not surprising that ClickHouse relies on column-oriented approach. So it stores data in columns. And every column is stored in a separate file. And this gives us an easy way to add and to remove columns, and also select only particular columns for the queries. And also ClickHouse is a truly columnar database, because not only it stores values of that column on the disk next to each other, but also it keeps those values on the disk clean without no extra data attached. And this allows us to use the next ClickHouse feature, effectively data compression, because each file will contain the same type of the data, either as integers or timestamps or some other type of data, but you can apply specific codecs for the data to compress it effectively. And once we have the data on the disk, we need to navigate it. And for this, ClickHouse relies on indexes. And you might wonder, like, what is new? We use indexes everywhere, right? However, indexes in ClickHouse are quite different, or at least quite unusual to me. For example, let's start with the primary index, which is also called a sparse index, because it doesn't really index every line. Instead, it indexes every 8,192nd row, and this number makes a bit more sense if you look at it in binary. And we use a sparse index because in analytics, we often have to deal with millions of rows, and we just can't afford to think in terms of individual items, values. So we use big blocks and we move through the data block by block, and this makes it faster. However, this has its consequence, because if you are looking for a specific item with some specific event ID, then you can quickly navigate to a given block. However, then you will have to iterate through those almost 10,000 items to find what you need. So we will talk about pitfalls later, but understanding the architectural characteristics of the system, it also gives you an opportunity to understand in which scenarios ClickHouse will shine and which one maybe not so. So primary index is very important for the speed of the queries. However, there always be queries which won't be able to benefit from the primary index. So we are dealing usually with different dimensions of the data. So for the online shop, we are having the time series data, so time can be our primary key. However, you also want to approach from the dimension of the URL of the website or some other criteria from the data. And in traditional transactional databases, we often would use secondary index. However, in ClickHouse, that won't work because we don't have rows on the disk to attach to secondary index. So ClickHouse has to be creative and smart of how to make those secondary indexes. And it defines the data which can be safely skipped when making a request. So this prevents the full scan of the column, because we can in advance tell, like, don't analyze particular data. And this is good for popular queries when you kind of can predict which data is frequently retrieved. For example, if you have an observability platform and you know that your users often retrieve some information about error 502. So you can look through the data through each block and check if does this block contain information about that error, and then put it aside. And then when the request from the user comes, you can actually predict which blocks should be processed and which ones should be omitted. So it's a pretty powerful feature, even though it might be not the easiest one to use and test. When it comes to computation and data processing, ClickHouse relies on their vectorized executions to be very, very fast. This means that during the processing, data in the columns are broken into pieces, and different cores are assigned to process that column data in parallel. And this allows to make computational faster. And I think it's possible to talk for hours about all the amazing things which make ClickHouse so fast, all the improvements, and if you are watching the monthly release webinars, they're amazing because they actually explain all that in detail. But I think we need to move on, because I wanted to show some other examples. And I hope that you are not too hungry, because one of the examples, we will look at the menus of a variety of restaurants going back into the 18th century. This data is collected and provided by New York Public Library, and ClickHouse documentation has an amazing, convenient set of instructions on how to use this data. By the way, I will be sharing all the links later, so I mean, you don't have to try to write it down now. So in that data set, we have 4 CSV files. We have the file for the menu item, menu page, and dish. And in ClickHouse, we use SQL to create tables in the database. And also we specify here the table engines that we use per each of the tables, and don't confuse it with a database engine. And table engines that we use, they define the features of that table. So here I'm using the merge tree, which is one of the, by far, the most popular table engine. And just to give you understanding how it works, let's briefly see how we insert data into the table if it's a merge tree or one of the merge tree family engines. So when we insert the data, it comes so that the chunk of the data which you bring, it is stored as a part. And then each insert will result in a part stored on the server. This makes it fast to write data into ClickHouse, because you can quickly, whatever you bring, you store it there, so it can be many parts. But of course, this makes it a bit difficult then to read, or at least not as fast. So what ClickHouse does in the background, it will merge those parts so that it is optimized for reading. And then we have more parts, and they will be also merged. And then the bigger parts also merged into the big one. Important to understand here is that sometimes merging will be never done. So what was not done during the background merge can technically be done during the query execution. So you can specify it. Yeah, and this is actually why when you send data to ClickHouse, it's better to send bigger blocks of data rather than small ones, because you can imagine if you start sending item by item into ClickHouse, that part combination will be slower. And there are a variety of members of the merge tree table engine. So the standard one, but also replacing merge tree, so that when we combine those parts, we replace the old data with the new data. So technically, you can emulate a OLTP scenario like this. Summon merge tree for also summon on top of it, and aggregating merge tree and others. So this is like super cool and also very fast. So yeah, to bring the data in our dishes and menus example, ClickHouse offers quite a bunch of tools, whether it is like CSV in our case, or TSV, JSON. Like, I think ClickHouse aims to work with almost any source of data that you have. And once we brought the data, we will have 4 tables in the system with data which is somehow normalized. And having normalized data is quite important for OLTP, to avoid data redundancy, preserve consistency, and use less memory. So we are all aware of that, and usually we tend to use it. However, the thing is, it's quite the opposite from the ideal state of data for ClickHouse. Because ClickHouse works with data differently, and it's not prone to the limitations of OLTP systems. So in ClickHouse, the more your data is denormalized, the faster will be your queries. And there are different reasons for that. First of all, we can have as many columns as we need, and those columns which are not participating in the request, they don't affect the performance. Also, the normalized data repeats a lot, so it's really good at compression, especially if the data is wisely sorted, and also if you use the right compression codecs. And also because we often don't update the old data, we don't have issue with breaking the consistency. So using joins, we can bring all the data into a single table, and joins are fully supported in ClickHouse. Yes, there are different join algorithms you can select from depending on your performance requirements and use case. So once we have all the data there for our dishes, we can do an experiment, and we can first try to get, this is just to show an interesting tendency which I noticed when I played with the data. So if we try to get the data for the year 1850 and we sort by the popularity and just select the data for potatoes, what we get is a list of very popular potato dishes for the people who lived in that ages. And you don't even have to read it. What I wanted to show is that when we change and we look at the same data for the year 2000, there is like an interesting tendency. And I was thinking, is it like a general that actually the length of the title is so way longer, or is it just a potato effect? For this, we can rely on ClickHouse and ask it to aggregate the data and to find a correlation between the length of the title and their decade. And if you run it, we can indeed see that later in times, the length of the titles is longer. Technically, it's not really a scientific experiment. There are so many different reasons why the titles are way longer later. But we can also look, for example, and find the correlation between the sweet or sugar in the title and how it corresponds, like the amount of dishes which are having sweet or sugar in it to the years. And to be honest, I really expected to see a clear tendency that we prefer sweet stuff later in the years. But no, it's pretty random. And if you're wondering what was so sweet in 1860s, it was just sweet potato. So moving on and talking about ClickHouse in collaboration with event-driven systems. And even though ClickHouse and Apache Kafka, for example, they are so different, but they do have so much in common because they both work amazingly well with immutable data and they both scale very well. So technically, you can bring the data into the ClickHouse using one of the available methods to store the data or to join ClickHouse and Apache Kafka. And here, for example, Kafka engine, and using materialized view as a trigger, which will react to new data, which appears in Kafka engine, and then you can transform the data or bring it as it is into a destination table. And there are there are different alternatives to Kafka engine. There is this new cool approach, ClickHouse Kafka Connect, or you can use JDBC connector as well. You also don't have to bring the data. You can make the request directly to one of the other, like to plenty of different data sources. Or you can also use dictionaries, which are super cool way to combine OLTP and OLAP together. I know that we are probably running out of time, and Flora looks at me. No. I wanted to stop briefly at what you need to pay attention to when working with ClickHouse. So ClickHouse is designed to be so fast. It's amazingly fast solution. But also you can think of the number of optimizations which are made that fast. solution. And of course, you shouldn't go against those optimizations. So I wouldn't recommend using ClickHouse for OLTP use cases. The sparse indexing, also the fact that right now it's possible to delete the data, but I don't know, maybe Alexey will disagree with me and tell later, but I think it's not the initial use case for ClickHouse. And also ClickHouse is not a key value database management system. It's not a file storage. It's not a document-oriented database. So the better the schema is, the faster will be your queries. So the schema really matters. There is a way to use a dynamically generated schema, I believe, but still, I think the better the schema, the faster the queries. And yes, this is the list of some additional materials which I used. And that's it for me. You can try also ClickHouse with Aiven.io. We have the platform with 11 different solutions, including ClickHouse. So we have all the integrations and tools to build end-to-end solutions with whatever you need, relying on open source tools and storages. That's it from me. Thank you so much for listening.
Questions?
If you have questions, you can ask them later. No, you can ask. Okay.
So you said when not to use ClickHouse. So when would you use ClickHouse?
So the question is for recording when to use ClickHouse. I think the ideal case is analytics. So when the data is immutable. But with all that, I want also to make it aware that there are so many different features which are added into ClickHouse, which, to be honest, looks like ClickHouse becomes the solution for everything. I would still say like the best, the one where you will just see the significant difference with other solutions is analytics. Yeah.
What is the benefit compared to like a data warehouse, like Snowflake, for example?
ClickHouse is data warehouse. So actually in these links, I do have a site of benchmarks, and you can compare how ClickHouse performs to other similar solutions. And I do believe it actually, okay, benchmark is very, very difficult and science where you can't believe anyone, but when using it in good scenarios, I think like that ClickHouse outperforms those other competitors.
Thank you.
So, I'm Alexey, and my presentation is about how to build a fast database. Imagine you woke up in the morning and suddenly you want to implement the fastest database. It should be ideally even better than ClickHouse. And what I will recommend to you is to simply drop this idea, because ClickHouse will always be the fastest database. But let's try to figure out why ClickHouse is fast. And it is very difficult to answer. There is no single reason. There is no single silver bullet. And actually, I'm not surprised that ClickHouse is fast. I'm surprised why every other system is slow. Why did not they optimize their code like I do? Okay, so I will try to present some ideas, principles, hand-waving behind these optimizations, and most of the time I will just do some hand-waving. Okay, so if you want to implement the fastest database management system, you want to use the best algorithms, and you want to implement it in the best programming language. For example, ClickHouse is written in C++, so it is fast, but maybe you should write your own database in C, and it will be even better. Maybe in assembly, because you know assembly is faster than C++ and C. So why don't you try? You should use the best libraries. For example, you might read some random internet page telling you that Apache Arrow is fast, Rust programming language is blazingly fast, and Synth.json is the best library to parse JSON. Also, you might notice that ClickHouse is not in-memory database. It stores data on disk or even in object storage. But you know that memory is faster than disk, so why don't write in-memory database and beat ClickHouse and win in every scenario? Maybe you should use coroutines. Do you know what coroutines are? Okay, don't even bother. But what will happen? The problem is that using the best algorithms is not enough. And the problem is there are no even such things like the best algorithms. So, again, what is the best way to process JSON, to parse JSON? The fastest library so far is Synth.json, and ClickHouse is using Synth.json. And Synth.json is implemented by this wonderful person. Look at his face. He cannot be wrong. And if Synth.json is not the fastest library, he will be responsible for that. And there is a benchmark on the internet named the fastest command line tools for querying large JSON datasets. And there are so many such tools: JQ, DSQ, TRDSQL, SparkSQL, Miller SpyQL, OctoSQL, and even ClickHouse can do it. Typically, ClickHouse is a database management system, but you can also use it from a command line to just analyze files. And here is a link to this benchmark. And what is the fastest database in this benchmark? Please tell me. Obviously. What? Obviously, it is ClickHouse. ClickHouse is fastest. So no surprise, we are using the best library, and we are the fastest. But the problem, it is not the reason. So we are using this library, but in a different context. And we don't use Synth.json to parse the input data. The question is, do we actually improve over Synth.json? The answer is yes and no. So, to parse JSON, ClickHouse is parsing the first records, and it is learning the data structure of these records. And then it does not parse the next records in a generic way. It is using specialized parsing for this specific data structure in runtime. And this trick makes your code faster than any possible imaginable library. You know, there is an old Chinese poetry. If you want to parse JSON faster, maybe you don't need JSON at all. So, if you want to make the fastest database, learn Chinese poetry. Okay, what about other algorithms like hash functions? Hash functions are everywhere, and we should hope that everyone optimizes it to the limit, and there is no possible optimizations left. So let's go to Google and ask, why Google? ChatGPT. Ask, what is the best hash function? And you will see these results. 1Q hash, the fastest quality hash function. What is the fastest quality? I don't understand. Okay, XX hash, extremely fast hashing algorithm. Strange. It should be extremely fast, right? Aqua hash, fast hashing with AES intrinsics. At least they have some charts for comparison. Okay, so what to choose? And again, the answer is not easy. Yes, you can test these hash functions in your scenarios, but there are a lot of different scenarios. You can use hash functions in hash tables, Bloom filters, hyperlog logs, and even as a function in SQL. So the users of your database will be able to write, select my best hash function of something, and it will be fast. But then there is one very subtle problem. So imagine you selected this, my best hash function, and you added it to your SQL language. And it is fast. But your users want to use it everywhere. For example, to shard your data to different servers. You calculate the remainder of division of this hash function and put different remainders to different servers. And now, if you will aggregate by this hash function, or if you will use it in any other data structure, on each of the servers, the lowest bit of this hash function will be unused. So you make it faster in one place, and it started to be slower in another place. Okay, what else? But how actually to test these hash functions? You should write a benchmark. Probably it will be a micro benchmark. And you should not test on strings of constant size. If you test on strings on 10 bytes, what about strings of 11 bytes? The test will be not exhaustive. So you should test on every data size. But the problem is, even if you test on every data size in a loop, if inside the loop the size will be constant, you will make the CPU branch prediction too happy about your code. I don't want CPU to be branch prediction to be too speculative about my code. Let my code surprise it every time. No. Actually, no. Yeah, I should not do this. But for the tests, you should use realistic distribution of input sizes. Like 90% of strings are empty, 9% of strings are less than 50 bytes, and 1% of strings like 1 kilobyte. Okay, sounds like I'm overwhelming you with too many details, and you will never want to implement your own database. Maybe this is my goal. But if you want, you should always look into details and be ready to everything that will stand out. So, how to do it? How many times you have seen that you loaded a website of your favorite company and it is loaded in 5 seconds, and you are disappointed. So, you press refresh and it does not reproduce. Everything is loading instantly. The problem is fixed by itself. Why do even bother? But if you are more curious, you will write a support request. Like, at this time, the website was loading in 5 seconds, and the support will answer you. It does not reproduce. Go away. Okay, so even this is not enough. But what you should actually do is to save every request in the logs with every metrics about everything. And then you might find the actual reason of this latency. Let's look at this picture. To the right, we have ClickHouse performance benchmark on 43 queries. I don't know why 43. To the left, we have the same ClickHouse server, but using object storage. And you can see that to the left, some queries sometimes are significantly slower. And it is easy to figure out because we have logs about every single query with every metric, like how many CPU cycles were used, how many page faults were used, how many data was actually read. It looks like this. And we see that the difference is about the data read from disk. So in one example, 0 bytes were read from disk. In another, I can like 2 gigabytes. And it is pretty easy to find the difference in the metrics. Okay. What you should also want to do is to have always on profiling, telemetry, and introspection. Did you know that ClickHouse has something like a debugger, GDB, built in directly into the database? You don't have to install GDB. If you want to look at what the server is doing at this moment of time, easy. Select from system.stacktrace. And if you at least once in a life have read ClickHouse code base, you will be able to figure out what it is actually doing. The system trace log is also an interesting table. It saves the data from the system stack trace periodically for every query. So you can find every place where query is spending your precious time. So what to do if you run a query and it takes 1 second? You know, 1 second is slow. Let me demonstrate. Like 1 second. Yes, it is slow. And you should ask yourself, why my query does not take half a second? If your query takes just 1 millisecond, don't be happy with it. Ask yourself why it is wasting 1 millisecond of my precious time. It should be faster. Maybe we can make it even faster. What else to do? Imagine it is a Friday night and you want to entertain yourself. It is easy with ClickHouse or with any programs that you are running. Run your program under strace, and it will display every system call. And try to explain every output. Okay, run a debugger. Look at stack traces, and again, explain why these particular stack traces show up. Run sudo perf top. Look at the assembly. Not many of you can read x86 or ARM assembly, right? But still try. It looks beautiful, and you will look smart trying to read assembly at Friday night, right? Okay, and when you will be able to explain everything, you can go to sleep on Monday. Oh, by the way, I'm assuming you don't have family. Maybe instruction will be different. Okay, another principle. You should design your system for real production workloads. You cannot design a fast database for production if you are sitting in your auditorium in a University of Database Engineering, Minnesota. I don't know if this university exists, but if you will do it, your system will be fast, on paper, or on synthetic benchmarks. It can break if you just apply it for production workloads, so be close to production. Apply it for as many different workloads as possible. Do quick iterations. Do quick releases. What about benchmarks? I hope you like benchmarks. I also like benchmark. Unless they are represented on some vendor-provided website. Because everyone is telling, like, my system is faster than everything. MongoDB is fast, right? Redis is fast. You go to their website, they are fast. You open the website of DragonflyDB, they say, no, we are faster. You open the website of Confluent, they will say, use Kafka, it is fast. You go to Red Panda website, they will tell you, no, use our system. And we also will tell you that, and I'm doing it every time. Yeah. ClickHouse is faster. Yes, we have vendor-provided benchmarks, but actually, it is much better if not you are doing these benchmarks, but if you let everyone on the internet test your system. That's why I'm collecting every independent benchmark for ClickHouse and trying to reproduce and improve. But not every system is as permissive. For example, in Snowflake acceptable use policy, I found this. You may not use our offerings in order to benchmark offerings or to build similar. Oh, I don't like it. By the way, they removed this item maybe after looking at my presentation. So please do benchmarks, do more benchmarks. Don't do benchmarking, but if you want, okay, does not matter. Do everything. Another principle, if you're trying to optimize something, you should have a lot of ideas, like hundreds of ideas. But be prepared that out of hundreds, just a few will actually work. So I tried to optimize our hash tables. I tried. Make CPU prefetching for memory. Use CMD instructions for comparison and probing. Do instruction parallel computations using Robin Hood hash tables. Using Swiss hash table algorithms. Nothing worked. But like seventh idea actually worked. My colleague implemented prediction of hash table size to save the work on resizes, and it worked. Okay. Another principle. Rewrite your code all the time. Don't be afraid of the changes. But what to do to actually afford this rewriting? You should use automated tests. And it does not limit to unit tests, integrational tests. You should also use fuzzing and sanitizers. If you are writing code in C++ or C, how many people are writing in C++ or C? Just 1, 2, 3? 3. Okay. If you write code in C++, something can break. And if you are not using sanitizers, I have bad news for you. Your code does not work. It's guaranteed to not working if you don't use sanitizers and fuzzing. For performance tests, it is also not so easy. Imagine you optimized some path in the code like 1.5 times. But if every other query degraded, but only by insignificant amount, like 1%, it is not good. So don't run just a single test. Automate performance tests. Let's look at one of the most recent optimizations. Runtime code generation for sorting by just-in-time compilation. It was 5 seconds. Now it is 4 seconds. Just 30% performance improvement by my colleague Maxim. So I asked Maxim, why just 30%? Why did not you optimize it like 2 hours? But actually it's a good optimization because you can see at this screenshot that we track every query. And even like single-digit percent matter if no other query degrades. Another principle, always test at scale. Test until it will break. And how do I use this principle? So, ClickHouse works pretty well on databases of 100 trillion records in production. And ideally, your tests should also run at this scale, ideally. But you cannot just go and load these 100 trillion records. They are loaded like events on the whole internet over the years. But we can improvise and take some public dataset. One example is Wikipedia page views statistics. Everything about page views of every page on the Wikipedia. It contains 370 billion records. Oops, actually, I'm not correct. It contains 450 billion records. This dataset has become even larger. And I have loaded it into ClickHouse. I just discovered this page and almost immediately decided, yes, I want this dataset inside ClickHouse. And I loaded it. And it loaded. And it went all right. I was not satisfied. I loaded it one more time. And I loaded it in 10 different ways, like loading from local files, loading from S3, using merge tree tables, replicated merge tree tables, replicated merge tree tables over object storage. And now ClickHouse eats this dataset for breakfast. Do weird stuff. Don't worry, this is not me. But he looks very similar. Let me explain why. Sometimes I want just more challenge. Everything works, everything is nice and cozy, and my queries are fast. How can I break ClickHouse? It should break somehow. And there are some beliefs from Olena, for example, that ClickHouse might be not the best solution as a document-oriented database. I want to challenge this belief, so I loaded HTML pages into ClickHouse from 5 million websites. And surprisingly, it went all right. Maybe ClickHouse is not good if you insert just a single record frequently with high frequency from random web pages from user browser. I want to challenge that. And I did exactly this. I implemented like a paste bin service, pastilla.nl. It is a production service. I recommend using it. And I also persuaded all my colleagues to use this service. And now I definitely know that ClickHouse is good for this sort of weird stuff. Another example, what about doing 10 million HTTP requests from ClickHouse with URL table function? I tried it, and it did not go well. But we have fixed it, and now I can do it every day. ClickHouse is probably not good as a key value database. ClickHouse is not a streaming data processing system. It is not a system for full text search. So ClickHouse is not Kafka. ClickHouse is not Elasticsearch, fortunately. But please hold my beer. Read the roadmap. By the way, not for 2022. Read the roadmap for 2023. Because we want to take some random items and try to do it. What about ClickHouse for AI, for vector search with vector embeddings? Maybe tomorrow, maybe next week, there will be a presentation by me named ClickHouse for AI. I just tried it, and it worked. It worked better than any other system I tested. And one of the last, always have fun. How can you be a database developer, a database engineer, if you don't have fun? You will not write a single line of code without having fun. So please, welcome, try and write your next system. You want to take, do it. How to have fun? Do basically whatever you want. I don't know, maybe you just want to slack from your work. Maybe you have something like ADHD, I don't know, it doesn't matter. Because in this case, you can do something like take 1 trillion prime numbers and load it into ClickHouse. I did that. I don't know why. I don't know for what. How can I apply the results? But I was just expecting to see something interesting, and the process of loading these 1 trillion prime numbers was actually very enjoyable. And actually, it had some benefits. I tested ClickHouse CTO, merge tree over object storage, and replicated databases. By the way, a question for you. What is it? What is this query? What should it do? Read carefully if you... What is it? Yeah, absolutely. It is FizzBuzz in ClickHouse SQL. The question is it fast? Here is another query. It looks way more complicated, but it is doing the same. Is it faster? I will not tell you. Because I don't want to steal this fun from you. Just install ClickHouse and try it. It is very interesting. So, how to write a fast database management system? You should use good algorithms in good context, always dig into details, measure everything. Work close to production, do benchmarks, more of benchmarks. Always do experiments, tests at scale, do weird stuff and have fun. And finally, get a life. Start contributing to ClickHouse. Thank you. Questions about the fastest database?
Is it fast?
A FizzBuzz?
Is it fast?
What?
ClickHouse.
ClickHouse. Yes, it is. But you should not believe me. Always test. By the way, what company are you from?
I'm from the Netherlands.
The company.
Oh, company. I have my own startup. Unwind data.
Okay, you should use ClickHouse.
I will try.
Was the answer going to be any different if it was another company?
For example, ADN, or how to pronounce it? ADN. Do you use ClickHouse in production?
We use Druid.
Bad choice. How I can help you? How I can save you from using Druid?
When you mentioned multi-tenancy at scale, right?
Mm-hmm.
Which is how we do stuff. We do multi-tenancy on top of one installation of Druid.
Yeah, and with ClickHouse, it is actually pretty easy. There are user access control, quotas, limitations on query complexity. You can have a large cluster and serve large analytics queries and short real-time queries. But for Druid, actually, my advice, if you are 100% satisfied with Druid, which is very unlikely, just keep it as is.
We'll try it out and let you know.
Okay.
You
you were talking about using production data. How do you manage getting that much production data without violating data privacy?
There is a specific tool built into ClickHouse named ClickHouse Obfuscator. It is processing some data, maybe from production, and managing to keep all the data distributions, like the number of distinct values, the average length of the strings, the correlation between values, but make these values actually made up. So it is safe, and you can export your data for testing, even if it contains PII. But maybe you should just remove the columns with PII and use only anonymized data.
What's the largest installation of ClickHouse in the world? I know Cloudflare uses a lot. Who else has like very, very big installation?
I think maybe the biggest installation is TikTok, ByteDance. They use several thousand servers. They even sometimes patching ClickHouse and sometimes creating issues when their patched ClickHouse does not work well.
How do they orchestrate this setup? Like how do they distribute the query and orchestrate the query?
There are multiple options. For example, if you want more trouble or you are an expert, use Kubernetes. If you want slightly less trouble, just use a couple of EC2 servers. And most of the time, you will be fine with just two servers, two replicas in different availability zones. You install ClickHouse on one server, on another server, create replicated table, and most likely it will be fine for your data volume. By the way, what data volume you are? Data volume. Mm-hmm.
Hundreds of terabytes.
No problem. Maybe you will need slightly more than two servers, all right?
Yeah, then how to orchestrate the query.
Just send queries with any driver from your application. That's it. What else you want to do? If you want some periodic queries, there are a lot of tools. If you want to do ETL, ELT, whatever the difference is, use your favorite tool, and most likely it already integrates with ClickHouse.
How do I use new Kafka connector? Could you provide like exactly one semantics with Kafka ClickHouse interaction?
There are some rumors that it does provide exactly one semantic. The problem is I don't believe rumors. So how exactly does it is it supposed to provide this exactly one semantic? It is using ClickHouse Keeper with a special like key value database that is using distributed consensus. And every batch that we are going to read from Kafka and insert into ClickHouse is recorded in Keeper with one of three possible states. Like we are going to process this batch, we are successfully processing this batch, and something in between. And next, we should actually activate our imagination and try to find every corner case. So supposedly, it should have exactly one semantic, but let's be very careful with these statements.
So you've touched on a very interesting topic. You optimize one function and it runs 2 times faster, but overall performance dropped.
Mm-hmm.
And you said you just rejected this change. How do you ensure that you didn't end up in some kind of local optima and you're always improving? And didn't you end up like program yourself in a corner with your current architecture.
Yeah, understood. Sometimes I have to do not optimizations, but pessimizations in the code when something is working incorrectly, and I have to fix the bug, and I see performance drops. What should I do? Maybe I should just accept it, but maybe I should try to find another optimization that will cover this specific case. And for some local optimizations, it is not easy. Sometimes you should not focus only on low-level stuff. Sometimes you should look in general. One example is like block-level hints. So for every block of data, going through the data processing pipeline, we also calculate the boundaries and use these boundaries for operations like group by. Actually, it is an obvious optimization, but it is slightly out of the box because it is not like deep C++ or SIMD instructions. It is looking at the system as a whole. It is trying to find a way to make everything better.
Last question?
You mentioned ClickHouse Keeper. Is it production ready and we should switch from Zookeeper and remove it from ClickHouse service?
Absolutely.
Absolutely.
It is production ready. It is used in production for like 1.5 years. We did not find any corner cases, any bugs in like maybe a year. And it has multiple advantages over Zookeeper.